All right, welcome back. This is another requested video, so again, thank you very much for the request. And what we have here is a very interesting problem where I've got a variety of proton NMR, carbon-13 NMR, and two-dimensional NMR, along with an IR and a mass spec, that I'm going to analyze and sort of discuss. This video is probably more tailored towards master's level organic chemistry or definitely advanced organic chemistry. The NMR data that we're going to be looking at is very complicated. So you could take this as a lecture on two-dimensional NMR, because we're going to go through a variety of two-dimensional NMR, COSY, HMQC, HMBC, and one other heteronuclear two-dimensional NMR. So this is going to be a lot of 2D NMR. The goal of this problem is to assign this structure. So we are given in this problem, we're given this chemical structure, and then using the data, the NMR data, we're going to be able to assign all the protons and carbons to their respective proton or carbon NMR. So we've got a proton NMR here. I've got my carbon-13 NMR right below that, and then for each of the peaks, each of the signals, we're going to assign which carbon or proton goes where. So I've also got an IR and a mass spec. We're not going to use this very much for determining the assignments, but it's just something good to sort of have a check. I've labeled a few things on here. So C10H7NO3, that's the chemical formula. And if you calculate that out, that's this mass peak here at 189. For these other mass peaks, these other fragments, you can start breaking things off. So 161, to get to a 161, we're going to break off, if we look down here, we're going to break off this carbon and the NH2 group. The remaining fragment should equal 161. So each of these big peaks, we should be able to do that exercise for, for the 121, 92. We can figure out what fragment that is, which is somewhat useful, I guess. In the IR, I can see that we've got probably this NH2 peak here, this peak at 3240, that's probably the NH2 spike, 3093, that's probably sp2 hybridized CHs, but again, less, I think, important for this problem. This is definitely more of a two-dimensional NMR problem. So let's go ahead and get into it. First thing I'm going to do is sort of just look at this proton NMR, get oriented, maybe do a few assignments if we see something that's very obvious. And the first thing I'm going to notice is I've got this aldehyde peak here. So out here, sharp peak at just past 10. I think pretty clearly that's going to be this aldehyde peak. I'm going to label this as an HA, so I can label that as my aldehyde peak right away. For my aromatic region, I've got 4 peaks. I've labeled the solvent peak here, so this tall singlet here, that's definitely solvent. And then I've got 1, 2, 3, 4 other distinct peaks. They all look like they integrate to the same value, probably 1. And that 4 aromatic protons, that's going to be my peaks here, 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 and here. For the NH2 peaks, I've actually got 2 signals, which is quite interesting. And we'll talk more about that as we move on. But I've got this peak here and this peak here. These are both for the NH2 group. Again, we'll talk more about how we get those 2 peaks there a little bit later on, but we're going to call these B. We'll end up calling it B prime and B double prime, and then I labeled these as C, D, E, and F. So we'll be using these labels as we move forward. So then these aromatic protons, I might have a guess as to which one this one is, but these ones it's probably a little bit unclear at this point in time. But for now, I'm just going to say that my 4 aromatic protons are going to be C, D, E, and F. That's going to be here. And then we'll talk more about this NH2, the splitting of the NH2 signal a little bit later on. But that's going to be my labeling for that. So the next thing I'm going to sort of just look at briefly is my carbon-13 NMR, and I've got some depth experiments here. So these 2 experiments here are showing us which carbon, so this is my carbon spectrum, right? So these are, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different carbon signals for my 10 different carbons in my structure. So I've got 10 different signals here, and then these signals, the ones that are at like 117, 125, 126, all of these signals, since it's the depth experiment, are telling me that these are the carbons that have actual protons bonded to them. So this carbon here that has this aldehyde proton, I already know that that's going to be this one here. simply because that's sort of where aldehydes, where the carbons for an aldehyde are going to be. So this carbon here, I can tell is this signal, and this dept is telling me that these carbons, 1, 2, 3, 4, 5, are the carbons that have protons attached to them. So then these 4 signals here must be the carbons in my aromatic ring bonded to F, E, D, and C. That's what this is telling us. But eventually, we're going to be able to label all of these, assign all of these signals to the different carbons and protons in my structure. All right, so let's go ahead and move right along. The other thing I'm going to show you before we get into the two-dimensional NMR is that I've organized this picture and the signals in this way. So I've got my proton NMR signals, where they come. These are the chemical shifts. And I've done the same thing for my carbon-13 NMR, and as we move along, I'm going to fill in essentially what all of the assignments are. We talked about our labeling of our protons, A, B, B prime, B double prime, C, D, E, and F. And then I numbered my carbons. So 1, 2, 3, 4, so on and so forth, to number all the different carbons. And then we're going to be trying to assign all the different protons and all the different carbons to these numbers, basically. All right, so let's move along to our COSY. The COSY is the most reasonable one to start with. So what the COSY is going to show us is the proton-proton coupling. And essentially on this axis, I've got my proton NMR. And then on this bottom or top axis, again, I would have the same proton NMR. So the cross peaks, these peaks here, that just should just line up with our actual signal. So we're definitely going to be seeing those. So those don't really tell us anything, right? It just tells us that, that signal is that signal. But then these 3 peaks here and these 3 peaks, it's sort of a mirror plane, that's going to be telling us what the correlations are. So over here, let's fill these protons back in, H, 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 and H. And then we're going to be able to correlate, so, this signal to the next signal, this signal to whatever else it's bonded to. Whatever else it's correlating to, I guess is a better way to put it. So when I'm analyzing COSY, the thing that I like to do is just sort of make like a data table, I guess. So I'm going to start by saying I've got a peak at 8.2, I've got a peak at 7.6, I've got a peak at 7.3 and 7.2. And then I'm going to make my table here. So then 8.2, 7.6, 7.3, and 7.2. And I like making a table like this. It's going to end up, it's sort of funny, it's going to end up looking exactly like what we have here. But for me, visually, it just is helpful, I guess. So you don't have to do this, but I definitely would encourage you to do it when you're first getting started. So I've boxed out my peaks that correlate 8.2 to 8.2, 7.6 to 7.6, and that's really the peaks that I've circled here. And then what I'm going to do is I'm going to start saying, well, which ones are which? So 8.2, this is my signal 8.2. The cross peak here, whichever it correlates to, that's going to be telling me that there's a correlation between that 8.2 peak and then whatever this peak is here, which is 7.3. So this peak at 7.3, right, that peak there correlates with the 8.2, so I'm going to put an X there. For the 7.6, I've got 2 correlations. I've got a correlation to 7.3, and I also have a correlation to 7.2. So I'll put X's there and there. I can do the same thing for the other side. So for 7.3, that's going to be this peak here. It should correlate to this peak at 7.6. And it's also correlating to this peak at 8.2. So if I'm just going along this right here. So this would be my peak at 7.3, correlations to itself, obviously. And then here's the peak at 7.6. And then here's the peak at 8.2. So I'm putting X's in there as well. Now, the last one for my 7.2 peak, that's this one that's furthest up, it's just correlating to here at 7.6. So this would be my diagram, essentially. And this sort of mirrors what I have here, right? I've got 3 peaks here, I've got 3 peaks here. That's sort of what we're seeing here. But this, I think, is just an easier way for me to visualize what's going on. So this 8.2 peak, what that's telling me is that whichever signal whichever signal corresponds to the 8.2 peak, it's only correlating with one other signal at 7.3. Essentially what that's telling us is that the peak at 8.2 is either this peak here that we've labeled as F, so let's keep our colors straight here. So this is F, this is E, this is D, and this is C. So what we've figured out so far is that the peak at 8.2 has to be either F or C. And the reason for that is that it's only correlating with one other of the signals. Same thing for 7.2. It's only correlating with 7.6. So C and F, we can tell, is going to be 7.2 or 8.2. The other peaks, E and D, they should correlate with both F and D. So we can tell that 7.6 should be either E or D, and 7.3 should be either E or D because it's correlating with multiple different signals. Now at this point in time, what I would encourage you to do is make an educated guess as to which one is which. And I'm going to say that this peak at 8.2 is going to be our F proton. We'll do that with green. And that the peak at 7.2, therefore, has to be C. And I'm going to label those on my COSY. I think that just sort of helps. You could label it over here as well. We could say that this one is F, this one is C. Now, I chose that because I know that I can draw a resonance structure here that would put a negative charge in the oxygen. I can just move these electrons here, move these electrons here, and that would make this have a positive charge for my resonance structure. And that would shift my chemical shift downfield. So I think that that's a good educated guess, and I think that's a good starting point. Now, as we move forward, sometimes you'll find, oh, something doesn't make sense, something doesn't work out, and that's okay, right? You just have to go back because we know that this one has to be F or C, right? And this one has to be C or F. So if you find later on that there's a conflict or there's something that doesn't make sense, then you can go back to this point and you can say, okay, well, I'm going to switch that and then run the problem again, because it has to be one of these answers, right? 8.2 it only interacts with one other, only correlates with one other proton, so it has to be F or it has to be C. So I'm going to start with this. If that's the case, then our 8.2 peak, that says we're going to have a correlation with peak at 7.3. So essentially what that's telling you is that if we say that this is F, then that means that E must be the peak at 7.2. So this peak here would be E. Now, for that E peak, that's the peak at, or excuse me, I think I said 7.2. That's the peak at 7.3. So the 7.3 peak, that should correlate with 8.2, which it does, and also with the 7.6 peak, which then would be D. So we could go back through this, right, and we could say, well, if we're saying that the peak at 7.6 is D, so 7.6 is D, then that should correlate with E and C. So that should correlate with 7.3, which is E, and 7.2, which is C. Hard to keep everything straight. So that's our COSY. So hopefully that makes sense. I know it's a little confusing. I guess just try to reiterate one more time. The 8.2, it only correlates with 7.3. So if we're saying that that's got to be one of the ones at the end. So that's telling you that E must be the 7.3 peak, right? So that's going to be 7.3. Maybe it'll be helpful to put in, this is 7.2, 7.3, 7.6, and 8.2. That might be helpful to then be able to draw those correlations that we want between the letters and the actual chemical shifts. All right, next is the HMQC. And now the HMQC, this is going to correlate our protons to our carbons. So this is going to tell us when we see these correlation peaks, that's going to tell you this proton, whichever proton this is, that correlates to this carbon signal. So this proton here would correlate to this carbon signal. So from up above, we said that this one is going to be F, this one's D, this one's E, and this one's C. And then I can draw those correlations to my carbon NMR. So this C peak, that's correlating to this peak over here at 117. So I can tell right away, if I go back to my master diagram here, that this peak at C, it's correlating to this carbon that we would have labeled 7. So from this COSY NMR, I'm going to call this peak 7. So maybe we'll do it this way so you can see what's going on here. So there we go. So if we've labeled this peak as C, that's my proton at C, and I've got this cross peak here with the carbon NMR at 117, then that's telling us that this signal for the carbon NMR is this signal here, this carbon here. So we're going to label that one as 7. Now for E, that corresponds to this proton and carbon number 9. And if I look at this, these two carbon peaks are very close to one another. So I looked very closely at these, and this one looks to be slightly higher up. So it looks that this one is a little bit higher than this one over here. So I said that this one was probably the 125. 125. It says 125. Let's make it so it's legible. And that this one was the 126. And then this peak here, that comes at 134. So if we're saying that the 125 it corresponds to E, if I look over here, that means that that would be number 9. So we'll put 9 on the top, 125. And then 126, that corresponds to F. So on here, that's number 10, 126. So I've already labeled this as proton F, right? So on my diagram here, that's proton F. So in the carbon that's bonded to proton F, that's going to be our peak here. So that tells us what the assignment for that carbon NMR is at 126. So that's the information we're getting from our HMQC. Oh, there is also, we forgot about our aldehyde. We already sort of knew that though. So this aldehyde peak here, that's number 1. So on our carbon NMR, that's going to be number 1 there. So that peak at 190. So at this point in time, we can start filling in some of the information on here. So we already said that number 1 is going to be 190. And then for our proton NMR, so let's just do that first. According to our according to our COSY, 8.2 is F. So hopefully you can see that. 8.2 is F. 7.6 is D. 7.3 is E. And 7.2 is C. So these correlations, right, that comes from our COSY. So hopefully you can see that. And then we can do the same thing for our carbon NMRs. So we've got some peaks here. So 7 is here at 117. So 117 is 7. And then 125 is 9. 126 is 10. And then we already filled in, and then this 134 should be D, which is 8. So for those of you who are still following along, those should be our correlations so far.